All right, now we come back again to this machine data science course. Now we are getting towards the end of the course gradually because we want to climax this particular course with machine learning, and we want to look at the background or introductory section of machine learning before we go to the practical section. Right, so we want to look at definition and the types of the machine learning that we have and other parameters that we need to learn to know about machine learning, how we measure the metrics and the performance, and another thing that we can learn before we go to the practical section. All right, so you're welcome again to this. So by definition, what is machine learning? Machine learning is a part of its larger domain, which is AI, artificial intelligence. It deals with algorithms that learn from given data and make predictions. The machine learning is part, okay, it's a part of AI. So, but its focus, attention is on algorithm development. The purpose of that is to predict data or given data. So this algorithm, they learn from data supplied to them, they learn from it. They were educated through the data supplied to them, and through that data and the model they built, this make predictions. Generally, machine learning is about making predictions. So, and through the data supply to them, so model is developed and the prediction are made. So let's go deeper. We have some types and application of machine learning. We have supervised, we have supervised. We even have more than that. We have a reinforcement learning, but we are not looking at that under this section because it's not part of this course. Under my supervised learning, we have what is called classification and regression. So under classification, example of such is or application is under fraud detection. We have image pair detection. We have diagnostics. We have image classification. Under regression, we have risk assessment, score prediction, and so others. Under unsupervised learning, we have dimensionality reduction. We have text mining. We have face recognition. We have big data visualization. We have image recognition. Under clustering, we have biology, city planning, targeted marketing. These are just example of our area of application of machine learning. So when it says supervised learning, it means a learning with a supervisor in a very layman language, a learning with a supervisor. When they say unsupervised learning, means a learning without a supervisor. It means no supervising agent included or involved. For supervised learning, there is a supervising agent involved. So that means there's a target uh, data or variable rather, and not just unsupervised learning, there's no any target variable. Or I can say the other way, I can say there's a for supervised learning there is a labeled variable, and for unsupervised learning there's no labeled variable. So whichever language you want to use to describe it, all are the same, but it's when you're now dealing with it practically that you now understand better what I'm talking about. So let's go further. We have, for example, we supply a given s1 comma s2 and y equals to label 1, label to label n, y is element of r, real numbers. A training set with many examples of s, y, the model learns on this example on the samples of this training set to produce the right value of y for an input of vector x. So s is a vector or matrix, which could be s could be a matrix, could be a vector. So and the y is happen to be the y-axis, y-x is the x-axis. We know that. So we use the word y as a target variable. Okay, y-x are the vectors or predictors. Okay, so these are the things that we need to understand. And we under calculation we see that y could be binary sometimes. Okay, Could be yes, no, 0, 1. That is a predictable values. We have yellow, we have gray, we have chunk, no chunk, we have increase, unchanged, decrease. These are the three groups. We have blonde. You know, when you look at if you remember very well when you are dealing with statistical analysis, variables, and the rest of them, we deal with a categorical variable. If you remember very well, that is exactly what I'm talking about. Categorical variable are majorly a good example of a target variable of y. So when you say y, what y is all about? Y is a target variable. Simple. In the very layman language, y is a target variable. It's a categorical variable. All right. So it could be yellow, red, male and female. All right. Yes, male and female, and the rest of them. That is y. So and the under regression, y could be temperature. Okay, could be number of visitors, could be number of kilometer per watt, number of price, number of hours work, and the rest of them. So which determine the changes, which determine what, because x determine what y is. So the changes of determine what y we predict, right? So if somebody work 10 hours, so what does that affect the salary paid? So all these things need to be look into later as we go into the practical section. So when do we use machine learning? We use machine learning when human expertise does not exist. For example, navigating on Mars. So in this case, machine learning are into. So most of those machines, they are AI based. They are intelligence machines. Okay. When human can't explain their expertise, speech recognition, we have a lot of now that has improved now, to different to different models. Okay, video to speech, speech to video, and the many things we see online today in ChatGPT, on AIs, audio videos that are going viral every day. They are machine learning based. Okay, when models must be customized or personalized medicine. Personalized medicine, they are based on machine learning. When you want to customize models for personalized medicines, when models are based on huge amounts of data, that is a genomics, or we call it big data analysis. So the machine learning is neat. Learning isn't always useful. What does that mean? There is no need to learn to calculate payroll. It's not everything we learn. Not everything we apply machine learning for. That's what I mean. So for example, you want to calculate the payroll, you don't need to learn machine learning for that. So you can just calculate payroll. But when human expertise does not exist in that area, then we need to do learning. All right, we have supervised learning, like I said before. It means a machine learning task of learning a function that maps an input to an output based on example input-output pairs. It infers a function from labeled training data consisting of a set of training examples. Now, a supervised learning has input label data. Now, when you see all this, when you are seeing their label data, our input data, we have label data, labels, cow, elephant, camel. There are three labels here now. There are three groups here now. Okay, these are labels. We have cow. So this particular data is grouped now, already grouped automatically. Okay, one of the group is cow, one of the group is elephant, one of this camel. So these are already labeled. We call it, these are target variables now, called target variables. All right, this particular variable is called target. You can call this one, for example, type of, you can call it animal type, for example. So then it means it has a supervisor agent. So training data set is passed, okay, because data is divided to training and testing. All right, so we have a desired output. When the data is wrong, it passes into the algorithm. Okay, this particular data now, this data, okay, supervising by an agent, pass to the algorithm. So algorithm passes to the processing. So we process everything to look at what is going on in the system. Then output is given by the elephant is going to this side, the cow down, and the camel there. So you can predict which one is cow, which one is elephant, which one is camel, based on the nature and the pattern of these particular animals. They have different pattern and different structure. So the characteristics is not the same. So the computer can be able to predict accurately, maybe we can predict 80%, 70%, 90% based on the power of the algorithm or model. So for supervised learning, there is no label. Unsupervised learning is a type of machine learning algorithm used to draw inferences from datasets consisting of input data without labeled responses. You can see here we have a lot of chunks of animals passed together here, but there's no label, right? No label in this case. So we use interpretation, unknown output, no training dataset contained here, all right? Algorithm is running, but data is processed. We have the output. Output will help us to separate the data into their different categories. This one does not deal with predictions. Okay, it only deal with clustering. It clusters the data into different groups. That is major work of unsupervised learning. So one of the example of that is logistic regression. Unlike regression here, the dependent variable is binary in nature. Binary means value is either 0 or 1, right? True or false. Okay, we have linear regression. Okay, before this, okay, also have a logistic regression. Yes or no. However, logistic regression is based on probability. There is a mathematical to represent. This mathematical equation to represent. So that is how it is. Yes or no. No. So we have a probability of half. This one equal to half. This is a threshold. Okay, everything from here up is yes. Anything from here from the 0.5 down is no. All right, so whenever the data cross the threshold, it is yes. Whenever it goes down before the threshold, it is no. So that is a regression, logistic regression. We have decision tree, which are generally a binary tree. So each node will only have two possibilities. It's basically an if-then structure that is continuous in nature. The algorithm works by recursively splitting the data into subsets based on the most significant feature at each node of the tree. All right. So is a person fit? Age is less than 30? If yes, you go to yes. If no, no. Eat a lot of pizza under here? Oh, yes, unfit. No, fit. Exercise in the morning? Yes, fit. No, unfit. So that is how it continues on down, down, down until you get a final answer. So that's the decision tree for you. We have random forest, which is an advanced of decision tree. Random forest collection of decision tree. It is a much bigger and robust version of a decision tree. Okay, decision tree have limitations. Okay, but in that mission is captured in and solved under the random forest. It can be used for both classification and regression problems. The reason is we can take more information than a decision tree. The problem of fitting in decision trees can be removed here, because decision trees has some problem of fitting, which random forest handles. All right, so you can see the structure of a tree. It's a tree-like structure as well. Okay, the same way with decision tree. Okay, it has a robust operation than decision tree. So we have support vector SVM, support vector machine, and it's a method algorithm that it could be also be used for regression in some cases. It uses to or more label classes of data and separate different classes of data by a what is called hyperplane. All right. So this in the middle here is called hyperplane. So that's how it separates data. All right. We have a maximum upper plane, minimum upper plane. So now we generate the optimal upper plane in the middle here. All right. So you have this now become the maximum margin. Okay, the margin between the negative upper plane and positive upper plane. Okay, it's called the maximum margin. So this data you are seeing here are called support vectors. It's also about support vectors. So the vectors are now being separated now. Oh, support vectors are being separated by the margin, or now a line is drawn in between the margin called hyperplane. So that is how SVM separates its own data into groups. And we have also ANN, artificial neural network, which supply input and generate the output. All right, so you can see the input layers here. Okay, this data supply data is now normalized, but a neural network is one of the operations that it uses, and that's data. The required data is normalized before it can be passed into the machine or to the model. So we have input layers, we have hidden layers, we have output layers. So we have final because it use the F1 is stand age, F2 is sigmod. All right, so input features S1, S2 here passing here, meaning to attended workflow build. The two of them, we have output layer probability that the person pass. So these are the probability greater less than 0.5 failed, greater than above passed. All right, so we have parameters, what they call hyperparameters in machine learning, which is a training process involves selecting the best or optimal hyperparameters that are used by learning algorithm to provide the best results. Now, when you model your data, you need to set some parameters to tune the model properly so that it can give you the optimal result. That is the purpose of hyperparameter setting. So you set the parameters. You have to do that repeatedly until you get desired result. That is the purpose of hyperparameter setting. So that is very important. And we have unsupervised learning as well. We have k-means clustering. So that's one of the example of unsupervised learning. Like I said before, this is not for prediction. This is for clustering or categorizing or grouping. Okay, the k-means algorithm is one of the most popular cluster algorithm. It classifies the data by dividing the samples into different k clusters of equal variances. The number of clusters must be specified in this algorithm as k. It is fast with fewer computations required with linear complexity. All right, so here we have k-means here after k-means. So before k-means, you can see the data like this. Then after k-means is now separated properly and groups. But you can see that they are missed different column. You don't know which one, okay, because they are not labeled, okay, not labeled. So now, when after the k-means is applied, it now help us label it by itself, okay. That is separated them into different clusters. All right, that is what they do. So we also have a hierarchical clustering, right? Which is used to alternative for the partition clustering, as there is no requirement for specifying the numbers of clusters to be created. In this technique, the dataset is divided into clusters to create a tree-like structure, which is also called dendrogram. So this is called dendrogram. All right, so in order to create this a tree-like structure, the dendrogram, the data are here. You can see different. This is one group, this is another group. So it gives us in different groups. All right. So we also have what is called dimensionality distortion, PCA, principal component analysis, commonly used in the field that deal with high dimensional data. When data is high dimensional, then you can apply PCA to reduce, not just reduce, you need to also maintain secure as many information as possible that they require. So without losing of information. So such as speech recognition, signal processing, bioinformatics, and so on. It can also be used for data visualization, noise reduction, and cluster analysis. So PCA help you reduce your large number of variables. You have 1,000 variables or less, 500 variables, 200 variables. You can supply to PCA. PCA help you reduce it without losing much of the information. That is what they call it. That is dimensionality reduction. All right. At the same time, it also give you a high result. I mean, optimal result. All right. So we have model evaluation and confusion matrix. Confusion matrix is a matrix used to determine the performance of the classification models for a given set of test data. It can also only be determined if the true values for the test data are known. For example, we have a simple table which predicts maybe a COVID patient, okay, or a disease. We have total, this is called n total prediction. So we divided into matrix here. This matrix, we have actual no, actual yes, predicted no, predicted yes. So we have true negative, false negative, true positive, false positive. Now, if you look at the definition of each of them, true negative means model has given prediction as no. Okay, model saying no, but and the real actual value was also no. Maybe somebody has asked a patient has a disease. So when you won't know that the patient has a disease actually, but you want machine to predict for you whether it is true or not. Machine say yes, it has, okay, or this person has no disease. He has this for this one now. It got true negative. He has no disease. Machine say yes. I mean, as say truly has no disease. So the machine no equals to the no of your real value, okay, or actual value. True positive means the model predicted yes that the person has a disease, and the actual value is also true. Okay, so it's called true positive. All right. Now, false negative means the model has predicted no, that the person has no disease, but the actual value was yes, the person actually have the disease, but machine classify as no. All right, that is called false negative. Then false positive means the model has predicted yes, that the person has disease, but actually the person does not have any disease at all. So that is a false negative. So these are the 4 parameters you must understand when dealing with machine learning under model evaluation. We call it confusion matrix. All right, this matrix, this was just 2 by 2. We can have more than if you have just because we have 2 groups, yes and no. If you have more than 2 groups, maybe 3 groups, it will be 3 here, 1 2 3, 1 2 3. All right. So we suppose we are trying to create a model that can predict the result of a virus that is either a person has that COVID or not. So the confusion matrix for this given as maybe you have a 100 runs, okay, then the machine, you say this actual no, actual yes, this predicted no, predicted yes. All right. After you have done that, you have a TN, FN, two positive, okay, false negative, okay, false positive, false true negative, true positive. All right. So this is our data. When you sum this together in this line, you have this. When you sum this together, you have this. When you sum this vertically, you have this. When you sum this vertically, you have this. All right. So from the above example, we can conclude that the table is given for the two class classifier, which has 2 predictions, yes and no. Here, yes defines that the person has COVID, and no defines that the patient do not have COVID. Patients do not have COVID. The classifier has made a total of 100 predictions. Out of 100 predictions, 89 are true prediction. 89 are true, which means true negative and true positive. If you sum this and this together, you have 89, right? And 11 are incorrect prediction, all right? Which is this and this, false, 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 false positive, false negative. They're incorrect. Don't forget here, if you remember very well, I say false negative, the model has predicted no, but the machine say yes. And here, the model has predicted yes, and the machine say no. So false negative, false positive, all right? But for true, it means they are both correct. So which is always 4 in this diagonal, okay? Why false 4 here, the true false here, all right? So always take note of that. So let's go back. Now, this is how you get to, when you calculate now your accuracy, you have to sum together 1 2 3 4, okay? You divide this one now, diagonal of true over total of everything, all right? So the model has given prediction yes for 32 times. Here lies yes, because yes, predicted yes, and no for 68 times. Say no 68 times, that is no. Whereas the actual yes was 27, okay, and actual no 23. But this is what model predicted, but this is actual value, okay. So you can see that is what it means. So let's see more example. Arbitrarily define one class value as positive and the remaining class as negative. So this is what I just explained now. Predict class, true positive, false positive, false negative, so true negative. So true positive, actual, and predict class is positive. Actual and predict class is negative here, and also here actual actual plus is positive and predict is negative, and actual plus is negative and predict is positive, which I explained just now. So you use this for statistics to calculate other evaluation metrics such as overall accuracy, true positive rate, false positive rate, and so on. So if you have data supply here, for example, that we did just now, okay, we have a yes, we have no, this is true, this true, these are predicted. No, this is swap now, okay? Predict can be here, can be here, can also be here, can be here, depending on the arrangement of your data. So just know which one you are dealing with. So this one remain diagonal, always true, positive, true, negative. All right, it's false positive, false negative. You can see. So for you to get your accuracy now, what do? You this plus this, right? This diagonal now plus this all over total of everything. That is your accuracy. Accuracy is 0.96, right? If you check this elsewhere, accuracy of this one, you have this together 0 plus 340 over total number of everything, right? Which is this. So we have 0.93. Let's say how to get accuracy. Okay, you have to first add this together divided by total. It's as simple as that. So we have two class values, predicted class values, number or on main diagonal correctly classified samples, number of off the main diagonal misclassified samples. So these are called misclassified. These are correctly classified, right? Take note of that. All right, so we have performance metrics. We have one of them is classification accuracy, which we just did now. It defines how often the model predicts the correct output. It can be calculated as the ratio of the number of correct predictions made by the classifier to all number of predictions made by the classifiers. That is total. So it means a two positive plus two negative, all the true, okay, all the true together. I mean, both two positive and two negative together over two positive, four positive, false negative, two negative. So this means summation of everything. Okay, here. So take note. We have also misclassification rate. All right, we call it error rate. So it terms error rate and it defines how often the model gives the wrong prediction. The value of error rate can be calculated as a number of incorrect predictions. So all numbers of predictions made by the classifier. So it means all the false, okay? All the false, this one for all the true, all the false of a total of everything. Okay, which means false positive and false negative of a total of everything. That is a error rate. All right, we have a precision, which is define the number of correct output provided by the model and or out of all positive classes that have predicted correctly by the model, how many of them were actually true. From those ones we say true, how many are truly true. So that is what precision is about. So we have a TP, true positive over TP plus FP to calculate how many of them are actually true from all the ones they say is true. So recall defined how to the total positive classes, how our model predicted correctly. The recall must be as high as possible. So the recall is very close to this, say T positive all over TP plus Fn, all right, which is a sensitivity. That's what it means, all right. So we have F measure. If two models have low precision and high recall, or vice versa, it is difficult to compare these models. So for this purpose, we can use what we call F-score. This score helps us to evaluate the recall and precision. At the same time, the F-score is maximum of the recall is equal to the precision. So F-score is 2 times recall times precision over recall plus precision. That's the formula of F-score. So we are going to stop here today and we will go for practical now to see how we can actually do some machine learning and how to can evaluate our model. And thank you so much for listening. I will see you in the practical class. Thank you.